Today I want to talk to you a little bit about some topics that we covered last year that are going to be important for your understanding this year, and we're going to start with a lab that we did last year. So one of the things we did was we took a buggy and we let the buggy roll across the floor. And you may remember this, the buggy looked something like this. If you didn't have physics last year, this might be a little confusing for you. So here's the buggy, and it had some wheels, and it had a little antenna. There was no one driving the buggy, but the buggy was cruising across the floor. And there was one thing that was really important about the buggy, and that's because the buggy was going at a constant speed. So when you looked at the buggy, as it was rolling, if you were to consider, let's say that there's like a little dude, there's a little dude inside the buggy, and what he's doing is, let's say he's dropping something on the floor. Let's say he's dropping like little bean bags on the floor. So every so often he drops a bean bag, and then the buggy moves a little forward, and he drops another bean bag, and then it moves a little forward, and he drops another bean bag, and he moves a little forward, and he drops another bean bag. What we can see is that these dots are equally spaced. And the fact that the dots are equally spaced is important because that gives us an indication about the motion itself. So, what did we do from here? How did we actually analyze the motion? Well, the way we analyze all motion is with some graphs. So the graph that we used for this one was a position time graph. It's a position time graph. And so, because it's moving in the horizontal direction, we say that this is the horizontal position measured in meters, and this is the time measured in seconds. Now, to begin this, we have to establish a zero line. So I'm going to put my zero line on here, and let's say the zero line is here. So the zero line is back there, but each of these dots represents a clock reading. And so let's say that this first one was 0 seconds, 1 second, 2 seconds, 3 seconds. What would the position time graph look like for this? Well, the position time graph for this one, at 0 time, he's already in front of the zero line. So that would look something like this. So what we notice is that the slope of this line is constant, which reminds us that this is a constant speed, because if we look at the slope of this line, if we just consider the slope as a general concept, the vertical is the change in the position, the horizontal is the change in the time. The slope is the ratio of the vertical to the horizontal. If we do a little bit of unit analysis on this, we'll notice that the units here are meters, the units down here are seconds, and that meters per second unit is analogous to the miles per hour unit. So in this case, the slope is the speed. Now, that's a general statement that the slope is the speed. We need to be a little bit more specific. Consider, what if the buggy was going in the opposite direction? If the buggy were, for example, out here, moving in the opposite direction, what would that graph look like? Well, if the buggy starts out here and is going backward, it started at a large position and went the other way. But the thing about this one is that the slope is negative, and speeds can't be negative. And so what we end up with is we need a more advanced concept for the slope. So it turns out that the slope is the velocity. The slope is the velocity. So in this case, because it's a constant speed buggy, we know that these lines are straight. We know that these lines are straight. And that's pretty easy to comprehend. If we want to graph, however, the velocity versus time, what would the graphs of the velocity versus time for this same scenario look like? Well, let's talk about the slope of the green line. The green line is straight. If I put my slopometer on here, what we'll notice is that the green line slope never changes. So the slope is constant, which means the velocity is constant. However, the blue, it has the same speed but the opposite direction, which means its velocity is negative. And so you'll notice within my ability to draw that, the green line and the blue line are equidistant from the t-axis, which means the speeds are the same, but the velocities are opposite. So one of the concepts, as long as your object is moving in one direction only, the speed is the absolute value of the velocity. If your speed is changing, and we'll talk about that next time, your speed is changing, it may look a little bit different. So our general concept for this works like this. If you want to find the average velocity, you calculate it by taking the change in the position divided by the change in time. Now, what I like about this is this could be negative, which means your velocity is negative. Oftentimes, to see the average, instead of writing average next to it, they'll put a bar on top. So V with the bar on top means average velocity. And then the last thing about this that's important is just as a person, one thing you should know. If you want to find your average speed, just divide your distance by your time. That's how we get our miles per hour. I don't like the way that they write miles per hour. They write it like mph in your car, which they want to mean miles per hour, but that's a little bit frustrating. It's more like miles divided by hours. So $60 miles per hour means for every additional hour that you travel, you're going to go an additional 60 miles.